My name is Sedigheh Eslami, and in this video, I will be presenting ArtQuest, Countering Hidden Language Biases in ArtVQA. Art is a fundamental aspect of human culture, and achieving visual question answering in the art domain is an important step towards conversational systems that can assist people. However, achieving ArtVQA is a challenging task since the model needs to understand the detailed visual information in paintings as well as interpret the natural language question and associate it with the visual data. ArtVQA also requires the model to possess historical background knowledge about artworks. Previous work has mostly focused on solving VQA for the general domain. In the art domain, majority of the papers have focused on vision language retrieval, image classification, captioning, and artistic image generation as downstream tasks. However, the field of ArtVQA with only one paper remains to be fairly uncovered. In this work, we employ a prefix language modeling approach for solving ArtVQA. In prefix language modeling, or prefix LM for short, given the prefix of a sequence, the goal is to predict the rest of the sequence autoregressively. In our closed-book approach, we encode paintings using a pre-trained visual encoder, and then encode the questions using a pre-trained language encoder. In order to unify dimensionalities of the visual and text embeddings, we apply one fully connected layer on the visual embedding. We then concatenate the resulting visual embedding and the question embedding, and use it as the prefix in our prefix LM approach. We also encode the answer and train for predicting the answer embedding given the vision language embedding prefix. We utilize a pre-trained language decoder for predicting and generating the answer. We also consider ArtVQA in an open book scenario, where the model is allowed to see an additional explanatory text for answering the question. We employ an image text retrieval approach in order to fetch the most relevant caption for a query image from a database containing art-related descriptions. In order to do so, we use a pre-trained text encoder again and encode all of the captions that we have in the database. Afterwards, we pick the closest embedding to the painting embedding using the cosine similarity. Once the most relevant caption is picked, we concatenate it to the question using this text template in here and encode the whole text using our pre-trained language encoder. The rest of the pipeline is as described as before, meaning that we concatenate the visual encoding and the text encoding and use it as the prefix for predicting the answers. In the next section, I describe our discoveries regarding hidden language biases in ArtVQA. First, let's have an overview about the AQUA dataset. AQUA is the first and only available benchmark dataset for developing ArtVQA. Questions in AQUA are either visual questions that ask about the content of the image, or knowledge questions that ask about some historical background knowledge around the artwork. We started our experiments on ArtVQA with the goal of understanding whether images truly matter for answering questions in AQUA. For this, we performed closed-book VQA using our prefix LM while ignoring the images. For language encoder and decoder, we used BART and T5 models. We first observed that BART and T5 with no fine-tuning are not able to answer the questions, meaning that these models do not possess any background knowledge in the art domain. However, after fine-tuning them, they achieve more than 70% accuracy without the presence of images. This observation shows that the images are quite insignificant for answering visual questions in AQUA. Furthermore, we use clip visual encoder and use images for answering questions. These experiments show an improvement of up to 8% accuracy in the VQA. This shows that our prefix LM modeling is indeed effective when considering images. For the knowledge questions, we tested both closed-book and open-book VQA approaches. We again ignored the images. In this scenario, we achieved In the closed book scenario, we achieve very low accuracy scores with or without fine-tuning. To our surprise, even adding the images are not helpful at all for answering knowledge questions in this setting. In the open book scenario, we engage two retrieval approaches for retrieving the relevant captions from the STEM art collection: question-based retrieval and oracle method. Furthermore, we only use the T5 model since it has been already optimized for open book QA scenarios. Our experiments show more than 70% accuracy for answering knowledge questions. These high scores alone are not necessarily an indicator of language bias in knowledge questions, since it could be that the captions already provide informative details. However, we observed that when adding the visual component and using prefix LM, the accuracy stays the same. This shows that the visual data is not playing an essential role for comprehending and answering questions. We also provide a few qualitative examples that show knowledge questions are independent of the images. For example, this question about when did Van Gogh live in the asylum does not really require this image to be answered. Given these shortcomings, we got motivated to create and publish ArtQuest. For ArtQuest, we harnessed the paintings and the structured information from the STEM art collection and manually created 6 initial open-ended questions for each painting about the artist, title, technique, school, time frame, and type of the paintings. In order to engender greater lexical variety, we employed ChatGPT with this prompt and rephrased our initial questions. This way, we ended up having 5 different phrased questions for each of the initial questions. For each painting among the 5 questions, we randomly selected one version to work with the painting. As a result, we have 6 questions per painting expressed in somewhat different ways across the paintings. We followed the same splitting from the STEM art collection for train, validation, and test sets. On the left side, you see the answer distribution for each question type, which also shows the majority answers for each question type. As can be seen, the answer distribution still makes it hard to obtain a very high accuracy when merely relying on priors. On the right side, we also provide the distribution of question length and observe that the majority of questions in ArtQuest include 5 to 7 words. We repeated the language bias experiments and evaluated whether the images in ArtQuest are important for answering questions. We observed that fine-tuning BART and T5 without the presence of images achieve about 20% accuracy. This is due to the imbalance of the distribution in ArtQuest that we saw before. When testing with the presence of images, substantial improvements of 30% is achieved. In the open book scenario, we observed that answering the questions when only using the captions reaches up to 63% accuracy. This is because the STEM art captions already contain background information about the painting. Nevertheless, adding images in the open book setting improves accuracy by up to 3%, concluding that the visual information provides additional information. For the baselines, we considered OFA and Bleidt for the zero-shot experiments, as well as Viking and our prefix LM when fine-tuning. In the prefix LM, we used the clip vision encoder and the language encoder-decoder from Plan T5 model. We observed that OFA and Bleidt achieve less than 5% accuracy, despite being amongst the top VQA models in the general domain. When fine-tuning Viking, it achieves 38% accuracy, whereas prefix LM model achieves 53% accuracy in the open book setting. We also show the performance of prefix LM for each question type category. Here we see that answering questions about the type of the painting is easier in comparison to the other question types in ArtQuest. We conclude the talk by hoping that our work motivates future researchers to enhance the research on ArtVQA and ArtQuest. Thanks for your attention.